transition a little bit out of some of the agronomic principles that we're going to talk about today, more into the soils aspect of it, and really kind of touch base on what's going on beneath the ground, and really take a look at the soil quality underneath that. So hopefully by now you're getting the message that soil health is about just healthy soil. It's not about cover crops, it's not about soil primers, it's not about those things. Soil health is just about keeping the soil healthy. So I kind of want to talk about, okay, well, what is the soil? What are we talking about? So I kind of start off with soil quality, which is maybe now the antiquated term behind soil health, but basically we're just integrating the physical, chemical, biological components of the soil and their interactions, right? What's going on right under our feet. So to capture that holistic process, we need to look at everything. We need to look at all parameters of the soil and everything that's going on right there. So where do we start whenever you go out someplace? Soil health, your idea on soil health or soil quality is going to be different from place to place. It's not always going to be the same. It's not going to be the same in Baca County that it is in Mesa County. It's not going to be the same. We did this yesterday up in Steamboat Springs. It's certainly not the same up there. So every place is a little bit different. So where do you want to start off? Where do you want to look at? Well, let's start to think about maybe like a baseline of where we're at. We're going to evaluate the context of the site. So one of the things that we can start with is go to Web Soil Survey. I'm sure everybody's heard of Web Soil Survey by now, and either get our soil map unit concepts, our soil component, or our soil series. And if you do go to the soil series, you can look at those official series descriptions which have all the listings for where you're at. It's a good place to start. But really what you should do is take a look around. You know, are there any signs of erosion going on around here? Can you look around and see anything? So step back and look at the landform. What sort of landform are you on? Are you on a mountain slope or are you on a valley fill? Are you on outwash? What sort of things are going on? What processes are occurring? What's the management history? You know, is this someplace that's been under traditional agriculture for the past 100 years? Or is this a mountain ecosystem? Slope and topographical features, of course, as a soil scientist, I always look at those things to kind of tell me more about what's going on with the water in the system. The climatic information. Colorado has this myriad of climatic things going on in it. It's one of the most diverse states of the nation when it comes to that. You go all the way from what we would think of, you know, arid environments all the way up to 55 inches of rain. Right here, actually, you know, outside of town. So it's kind of interesting whenever you think about the different precipitation that goes on just in Colorado alone. And then not to mention the fact that we go from 4,000 feet to 14,000 feet. So we also have this frost stuff going on, right? Frost-free days. Step back and look at your Huck-8 or your county or your watershed, get an idea. And also, is there anything environmentally sensitive going on in the area? Are there wetlands? Has it been in CRP? Is there something else there that we can key in on to get that site characterization down? So we have some indicators of soil quality that we can look at. The first thing, one of the most important things, is soil organic matter, right? SOM. And this gives us an idea of the fertility, the stability, the nutrient retention, any sorts of erosional processes that are going on. You can look at the physical properties of the soil, delve into the soil physics with the structure, the texture, the bulk density, which is a big important one, water holding capacity, right? And that's all relating to the nutrients and the transportation of water within that soil, the soil physical properties. Look at the chemical side of it. pH, the interactions that are going on underneath with your nutrients, EC, electrical conductivity, related to salts in the system, extractable NP and K. And of course, one of the most important ones whenever we're getting to soil quality is the biological. Sorry, so this doesn't work on the TV screen. Biological. And those microbial catalytic potential repository for carbon and nitrogen. Some of the more important things in soil health is the CN ratios and the carbon to nitrogen ratios. At the bottom here, I just kind of show some of the stuff that we can do in the field. The left over there is just a pretty simple slate test for small soil beds. Those are just filled with water and drop the ped in. In the middle, that's a nitrate test using the litmus strips that we can do in the field with the 1-to-1. We'll get into that a little bit more. And then over on the right, kind of looking at the the soil extraction process. So let's talk a little bit about some of that soil physical property stuff. Bulk density, right? This is a big important one because this is an indicator of soil compaction. What's going on out there on the ground, right? That the soil being compacted, because that affects the infiltration, rooting depth, available water capacity. Some people still refer to it as porosity, plant nutrient availability, and also that microorganism activity, right? Because as we squish out the soil, we're squishing out different things, not just compacting the soil. Bulk density is expressed in grams per cubic centimeter. So when you look at the soil reports or the soil map unit reports, that's what it's going to be in. So the scale where it kind of breaks at like 1.6, that's what it's going by. We know that the inherent factors can't be changed, right? So although this is all important, well, we can't change the texture of the soil. There's nothing we can do to affect texture. So we have to think about what's actually there that we can manage. You know, how can we manage the soil that we have? We can change the management practices that go on it, though, right? The things that the soil cover, and we want to increase the organic material, which will lead to better structure, less compaction, and greater porosity. So I have some graphs up here. Over on the left, these are the abiotic soil components that are found, 4 major components of any soil volume. You can see that air and water take up roughly 50% of any given unit of soil. Only 45% of that is mineral matter, which is that sand, silt, and clay, right? Or rock fragments. And then organic matter, and I put less than or equal to 5% because usually in healthy systems that's about where it's at, 4 to 5% OM. But in some places, in more arid environments, it's significantly less. And over on the right is the relationship between available water and texture, just showing the permanent wilting point as it relates to field capacity. And then with the textures on the bottom, the finer grain stuff as you move across to the right. What about the organic matter that's in there? There's the organic component of the soil, right? It consists of 3 primary parts: small plant residues, small living organisms, and the decomposing organic material. It's a reservoir of nutrients for crops. So one of the things we're talking about in soil health is maybe we don't have to add so much fertilizer, maybe we don't have to have so many inputs if we could just increase our SOM. And looking into those things is what we're getting into here, because we can estimate this in the field, and then we can extrapolate nitrogen, phosphorus, and sulfur contents from that. Over on the right is it's out of our StatsGo database. It's not our Surgo database, but this is a representation of kind of in situ soil organic matter distribution for the whole U.S. using just StatsGo data. So it kind of shows you the darker spots are obviously more organic material found naturally in the soil, and as you go to lighter or to gray, which is what the majority of the Southwest is, less organic matter. So the darker areas along the Mississippi River and further north into Minnesota and the UP, you can kind of see that that's probably pretty true. Now, Colorado, it kind of goes from the southwest corner, you know, gets a little bit drier, and then the upper forests have a pretty good deal of organic material in them. On the left, these are the major components that less than 5% from that pie chart. Now we're looking at that as a whole, and we're saying, okay, what's going on in there? Well, about 1/3 to 1/2 is stabilized organic matter, and about 1/3 to 1/2 is the decomposing organic matter, right, an active system. Less than 10% is that fresh residue that's occurring right immediately on the surface, and less than 5% of that 5% is living organisms, things that are going on. Can we manage it? Sure. Use cropping systems that incorporate continuous no-till cover crops, the things you've heard before, solid manure, other organics, compost teas, those sorts of things. Reducing or eliminating tillage, because tillage causes this flush of microbial action, immediate microbial action, like we just mentioned a little bit ago. As soon as you tear up the soil, all this oxygen rushes into the system that wouldn't normally be there, right? 25% of that soil is oxygen or air, and you flush it into the system, so it speeds up decomposition immediately. So as soon as you till it, it starts to speed up that decomposition, and you're degrading that natural process that's going on. You can reduce erosion by using appropriate measures, you know, the principles of soil health that we want to talk about. And you can do soil tests, you know, through the extension service or private. Here on the right, we have kind of this color chart that we've come up with, and you can find it at soils.org. It's kind of giving you an estimate of organic matter, and it's just like using a one-cell color chart. So we're kind of showing you there that there's some in-field tests that we can use to determine some of this stuff. I have this graphic up here because it's really interesting. This is 10 years of conventional till versus no-till on just organic carbon. And organic carbon expressed in grams per kilogram of soil over on the left, and across the bottom is soil depth. So we're going 0 to 5 centimeters, 5 to 10 centimeters, and 10 to 20 centimeters. The thing that stands out to me is that conventional tillage shows that organic matter, or that organic carbon content, remains the same, all the way down to 20 centimeters. But whenever you use a no-till system, you're seeing that there's a huge increase in the surface, the 0 to 5 centimeter stuff, and it decreases down to where it is in the conventional tillage system. So I think that's a really cool thing to look at, and it just shows you that if you don't disturb it, those organic carbon content really increases, especially at the surface. This is affecting soil respiration, as I kind of alluded to. This is just to measure the carbon dioxide released from the soil from decomposition, and that's the naturally occurring processes that are going on there by the soil microbes and the respiration from plant roots and other soil fauna. It's an important indicator of soil health because it kind of indicates that level of microbial activity that's going on in the soil. So we're looking at its content and its decomposition rate. It's an indicator of nutrients contained in organic material and things that are being converted to be available to crops or other plants that are naturally occurring. So can we interpret management practices or impacts on this SOM, the soil organic material? Sure. I showed the application here, and I'll pick on tillage. It stirs the soil, providing a temporary increase in oxygen, like we just mentioned, and it breaks down those carbon sources. What's the short-term impact? Well, it provides a flush of nitrogen, right, just naturally out of air, other nutrients, and then the carbon dioxide releases immediately after tillage because it's binding, it's burning up. So that in turn increases that decomposition rate of the residue and other carbon sources. But what's the long-term impact? Well, you have a natural steady decline of organic material over time because you're causing that every year. So that decreases the soil fertility, decreases all those naturally occurring plant available nutrients, and drives down your soil quality. So let's talk a little bit about electrical conductivity, soil EC. This is just a measure of the amount of salt in the soil, or soil salinity. Don't confuse this with sodic horizons. Salinity is slightly different. It will affect your crop yields, your suitability, nutrient availability, other things that are living in the soil. Excess salts hinder plant growth. Of course, that's a pretty big problem around here. And it affects the soil water balance also. Soils naturally containing excess salts in arid environments are pretty common, especially San Luis Valley Basin and then a lot of the western slope too. Can we manage it? Sure. Manage anything, right? EC is affected by cropping, irrigation, land use, applications of different inputs. The important thing to note is whenever you're doing this on irrigated land, water naturally, of course, has salt content in it too, so you're adding a flush of salt to an already saline environment. So you might have to use additional water to flush those salts lower than the rooting depth, but whenever it comes back up, the salt comes back up twofold, threefold, because of that water from the irrigation water has the salt occurring in it naturally. So salinity management becomes really tricky, especially in irrigated systems. Here I'm just showing the salinity classes in the relationship on a 1-to-1 EC. And it's interesting to break it down by texture, but I really like to just look at the bottom where I show all textures here and kind of give you that degree of salinity, or those different classes of salinity. And I'll kind of jump to the next slide because it breaks it down that way. So this is what we use out of our soil survey handbook. So when you look at our reports, these are the values that compare to the salinity class. So 4 to 8 is a slightly saline, probably pretty common around here. Anything over 8 generally starts to really pump up, and you really have to start managing it. It can influence growth. This is a pretty interesting chart. So it lists a lot of the common crops and then their threshold EC, right? So this is, again, a one-to-one electrical conductivity test. And if you pick on, let's say, alfalfa, the threshold EC for that is about 1.1 to 1.4. So that's your optimum growing environment. Every percent yield decrease beyond that is 7.3. So 7% decrease in crop yield for every 1 unit you go up in EC beyond that. So each time you go up, that number is going to double. So by the time you get to 2, it's 7.3. By the time you get to 4, it's 14.6. It's pretty impressive in your crop yield. Remember, you're talking about a whole hectare. What about pH? Does anybody know what pH stands for? Bonus points if you know what pH stands for. Close. Yeah. The potential of the hydrogen ion. So we're just saying pH is just a logarithmic scale, right? We look at it from acidic to basic on a log scale. It's one of the most commonly used log scales that we do. The measure of soil acidity or alkalinity. Important indicator of soil health. Why? Well, it affects our crop yields, suitabilities. Again, nutrient availability is affected by pH. We manage it? Yep. How do we manage it? Well, we introduce man-made nitrogen into the system. We introduce lime. We do different things to keep that pH range. And where do we want it? What's an optimum range for pH? Yeah, 6 to 8 is a good one. Here I've shown relative yields of those soil pH. I'll pick on alfalfa again. It's down towards the bottom, second from last there. This is right out of the soil quality book from SSSA. With 100 being the best and 0 being the worst, right? So alfalfa growing in a 4.7 pH, it's at 2. The relative yield jumps all the way up to 100 at 6.8. Most of them right at 6.8. We're right around 100 on almost all of them. And the scale doesn't go up beyond this because it's always generally more acidic systems, but it declines the other direction too. So just to show you that relative yield, just by 1 or 2 pH, there's a huge effect on your system. And here's why. This is the pH scale broken out on different nutrients over on the left and their availabilities. And I'm sure a lot of you have seen this before, but right at that 6.5 to 7, all those bands are fat. That's where all those nutrients are available to the plant for uptake into the system. And different elements will taper out at different pHs. So if you have something that needs multiple nutrients, which we always do, you can see that whenever one thing isn't available, it's going to have that drastically negative effect on your nutrient availability. So that's why we're always kind of driving towards that 6.5 to 7. At 6.8, which is optimum, that's a really great one, and this shows you why, because all those nutrients are available. So let's talk a little bit about those soil elemental processes that are going on. Soil nitrogen. It's the most abundant element in the atmosphere, right? 75% of air is nitrogen. It's the most limiting crop nutrient, though. And it's because the nitrogen cycle, everything that goes on in the nitrogen cycle has a different effect. So we're always driving towards nitrogen fixation of what's going on underneath the ground, right? Bacteria and legumes are doing this, and also through atmospheric deposition and rainfall. We also add it into our systems by fertilizer, manure, other organic materials, crop tea, or compost teas. What sort of inherent factors are affecting the nitrogen in the soil, though? Soil drainage. Well, it always relates to water, right? So soil drainage, soil texture, which will affect your saturated hydraulic conductivity going on underneath the ground. I say soils that have poor drainage and are ponded or saturated with water this can cause denitrification to occur. And then that results in a loss of nitrogen as a gas, which results in also emission of potential greenhouse gases and yields reduction. And it also increases your expense, right? The bottom line, the dollar, it costs more because you have to add more nitrogen, which is getting more and more expensive by the day. So here's the nitrogen cycle, or one representation of the nitrogen cycle. And I picked this one out because it showed the mineralization from the organic matter into ammonium, and then nitrification is occurring below there, and then it comes back up into plant consumption. Kind of the take-home message here, though, is that in the nitrogen cycle, there's more going on below the ground than there is above the ground. And I think we all know that, and I just want to kind of show that, runoff leaching still occur. It goes, when it runs down, kind of like that, the blue water that Joel was talking about, we lose out nitrogen too in that. We have a quick hand test that will be made available or may already be available. This isn't one of the things that was in Gempler's. This is a different, the soil bucket test. But basically what it is just these litmus strips, and they come in their own little jar and has a color scale on the side. Gives you a good, quick field estimate of the nitrate that's in the system. And it's just a one-to-one water test, right, or saturated paste. And all you do is just take the strip out and then dip it in and wait for it to turn pink and run along the side, much like a pH test. So pretty cool stuff is becoming available to test this in the field.
How accurate is that?
It's pretty good. I mean, for an in-the-field test, it's not going to be like sending it to Blacklands or anything, but it's going to get you pretty close. Phosphorus is the other major player that's going on. It's a major role in plants to store and transfer energy, right? Because they use phosphorus in photosynthesis and for growth and reproductive processes. And I show here the phosphorus cycle. I'm not going to really drive into it again, but I just want to kind of show the soil processes. What's going on beneath the ground, again, is more than the inputs or the above ground stuff. So it's important to note that what's going on underneath you, your soil inherent factors, play a pivotal role in the phosphorus cycle, the nitrogen cycle. Can we manage phosphorus? Yeah. It's a little bit slower. What does phosphorus do for us? Well, it promotes early maturity. It increases water use and efficiency, and also it increases your grain yields. So phosphorus deficiency can stunt vegetative growth, it can stunt grain yield. So we want to really manage it well. It's relatively stable in soil, moves very little compared to nitrogen, and really all the other elemental processes from here down kind of move a lot slower than nitrogen. Just show phosphorus deficient corn here, just a grass and what happens to grass. The purple color on the lower leaves, some of the stuff you might have seen before. Also the soil there, you can see some of the crop residue from last year, maybe 2 years ago, and also that bare soil. So we got more going on than just phosphorus deficiency there when it comes to soil quality. We can do a quick hand test here too with the phosphate. So again, the saturated paste or the one-to-one on the left, dipping your litmus strip, running along the side of the tube and getting a good field estimate. So putting it all together, what can we do in the field? What do we need to know? What are the important things? We're thinking about getting together these buckets for distribution, and there's a lot of good stuff in them, and there's a lot of literature in them too, but the important things are, you might be able to piece together your own. The important things will be in those litmus strips, some of the scales, the EC meters, the pH meters. So the soil health cadre is putting these together, hopefully for distribution to field offices. And we're just trying to show that the quality of the soil, as we started, is soil quality. It depends on a lot of different things. And a lot of those factors that are going on occur in the soil, the in situ stuff that you can or cannot change based on management or your soil inherent physical properties, soil textures, bulk densities by compaction and things. So detailed information, you need to look site to site. You need to really think, where am I standing, where am I at? What's different here than over there? Because those management practices might be different from site to site. So just kind of get you thinking about the different things that can go on beneath the ground.